We're now in section 3.5, and we're talking more about some different types of functions. So we've been talking about polynomials, and this unit we're talking about, or this lesson, we're talking about rational functions and what those look like and some properties of them, and specifically some of the properties that we're going to look at today are called asymptotes. Rational functions are built out of polynomial functions. That's why this lesson is in this unit. We've been talking about polynomial functions. All rational functions are fractions that are made out of polynomials. So it's a fraction where p is a polynomial and q is a polynomial. The top and bottom are both polynomials. The domain, we've talked a lot about domain. In lesson 2.3, we talked about domain. So if you go back and review lesson 2.3, that'll give you a better idea about where we're getting these domains from. We get the domains by excluding numbers. When we have rational functions, we're excluding anything that's going to make the bottom zero, because we can't divide by zero in math. So in this first example here, f of x equals 1 over x, x cannot equal 0, or else the bottom would be 0, right? And so the domain of that function is listed here. Everything from negative infinity to 0 and 0 to infinity. The second function we have here, what we could do is take the bottom. We can't clearly see what would make the bottom 0, but if you factored it, now you can see that x can't equal 3 over 2, or the bottom would become 0. X can't equal negative 4, or the bottom would become 0. And so then the domain is going to be everything except for those two numbers. In this final example we have on this page, we have x squared plus 4 on the bottom. If we try to factor x squared plus 4, we can't, and there's absolutely nothing that makes that bottom 0. X can be anything. Without making the bottom 0. And so our domain's not restricted at all. It's just negative infinity to infinity. Again, if this is not ringing a bell for you, what you need to do is go back and review lesson 2.3. All right, here's some housekeeping stuff that we need to take care of. We have talked in 2 lessons ago, we talked about this notation where x is approaching, f of x is approaching so-and-so. What these notations mean, this one, for example, is saying as x approaches c, the plus sign means we're approaching it from the right. So c is just a number. C is any number. We'll say c is any number. That number will be specified for you in the problem. It could say, for example, as x approaches 0 plus, that means x approaches 0 from the right. It could say x approaches 3 minus, that means as x approaches 3 from the left. C is just a number. X approaches infinity means x is getting really large in the positive direction. That's going this way. X is going towards infinity. X approaching negative infinity means x is getting really small, going towards negative infinity. And we want to know what's happening to y as x is doing these things, right? So y could be doing one of these things. Y could be going towards infinity. That means y is going upwards. Y could be going towards negative infinity. That means y is going downwards. Or y could be just going towards some number. So that would be like here, where y, as x goes to infinity, x is going outwards, right? As x goes to infinity, y is getting smaller and closer to 0. The y value is getting smaller and closer to the x-axis, which is closer to 0. I'm saying the y values are getting smaller as x goes out. Here are some examples. If we're looking for the end behavior of this one, as x approaches negative infinity, what is y doing? So x is 0 here, right? X is negative 1, negative 2, negative 3. X is approaching negative infinity. As x goes to the left towards negative infinity, our y value is coming down towards 0. Our y value is getting smaller. As x approaches 0, here's 0. This time we're looking at from the left specifically. As x approaches 0 from the left, x is approaching 0 from the left, the y value is going upwards towards infinity. As x approaches 0 from the right, as x approaches 0 from the right, the y value also is skyrocketing off towards infinity. And as x approaches positive infinity, that means x is getting very large. It's going outwards to the right. As x approaches positive infinity, the y value is getting smaller, closer to 0. There's a name for this line right here. It was on that landing sheet. This line that the graph seems not to cross, right, is called an asymptote. It's just an imaginary line that the graph is not going to cross. An analogy that I like to make is that it's like a rain gutter, where the rain is going to fall right into that rain gutter. It's not going to cross and splash across the other side. It's just going to follow the rain gutter, right? Follow it right off the edge of the roof. It's just going to follow that rain gutter out. Those are called asymptotes. Different functions can have more than one asymptote. They can have one asymptote. They can have horizontal asymptotes, vertical asymptotes. They could even have asymptotes that are slanted sometimes. This example does not have one that's slanted, but it has one vertical asymptote and one horizontal asymptote. You're typically only going to have one horizontal asymptote, but you can have multiple vertical asymptotes. This example only has one, right? We can see it clearly that is where the graph does not cross. But some functions do have multiple vertical asymptotes. All right, I would take a second, pause the video, and see if you could figure this one out. As x approaches negative infinity, our y value approaches 0. It's getting really close to 0. As x approaches 0 from the left, so from the left, I'm approaching 0. Look, here, actually, this is not on the 0. This is on 2. As x approaches 0, that's right here, right? And so our graph is actually at something like -1/2. Our y value is at something like -1/2. As x approaches 0 from the left, we hit right at -1/2. As x approaches 0 from the right, right there, x is getting really close to 0 right there, right? We're still approaching 0 over here, but we get even closer on this side. X is approaching 0, right there at -1/2. As x approaches infinity, our y value approaches 0. I know somebody has already written down for these, they've written down infinity and negative infinity. Let's look at y. If we said something like, as x approaches 2 from the left, as x approaches 2 from the right, let's see what those would look like. As x approaches 2 from the left, so here's 2. As we approach 2 from the left, x goes way down towards negative infinity. Y goes way down towards negative infinity. As x approaches 2 from the right, here's to the right, we're approaching our 2 value. Y shoots way up towards positive infinity. That's what some people were looking at when they wrote these in right here. But you have to pay attention to what number you're approaching. We're approaching 0 here from the left. Since we're approaching 0 from the left, that means we're trying to get close to this value right here. X is 0. All right, if we go back and look at this one also has a vertical asymptote. You can see it right here. Here's the vertical asymptote. And here's the horizontal asymptote. Again, it's like rain gutters that your graph is not going to cross. Sometimes they do cross the horizontal asymptotes, but it's not typical. But they absolutely cannot cross a vertical asymptote. All right, the definition of a vertical asymptote is where your function's either approaching infinity or negative infinity at that value. So this one has a vertical asymptote because if we look at right over here, your function's approaching infinity or negative infinity at that value, x equals 2. So then our asymptote is at x equals 2. that's where our function's approaching infinity. It's actually a vertical asymptote, in fact. Vertical asymptote at x equals 2 because that's where our function's approaching infinity. We see that here. Our function's approaching infinity at x equals 2. You can see all the variations of that here where x is approaching infinity at c, x is approaching negative infinity at c, x is approaching infinity coming from the right, x is approaching negative infinity coming from the right? It doesn't matter. If it's approaching infinity, that's going to be a vertical asymptote. The way you find those is by looking at the restrictions on the domain. So with that very first slide, we talked about the domain. We talked about what we really care about is the bottom not becoming 0. And so what we're going to do here is we're going to factor this whole thing. F of x equals, the top would be 3x minus 2. The bottom, we could do star method, and it would be x minus 2, x plus 1. So the first thing I want to look at is the domain. For what values is the function undefined? Well, we know that x cannot equal 2, and x cannot equal negative 1, because either of those would make the bottom 0, right? Those are the values for which our function's undefined. Again, go back and look at lesson 2.4 if you need to. That means the domain of this is going to be everything from negative infinity to negative 1, negative 1 to 2, and 2 to infinity. All right, now that we have that, we can start looking for our vertical asymptotes. The trouble with some of these is, most of the time when you have a discontinuity, most of the times when you have a break, it's going to be a vertical asymptote, but not every time. So this could be a vertical asymptote, could be. This could be a vertical asymptote. The issue is it removable or is it not removable from our problem? So in this problem, if we notice that x minus 2 will divide out top and bottom. So that's actually not an asymptote. If it's removable, then there's a hole instead of an asymptote. There's a hole at x equals 2. If it's not removable, then there's an asymptote at x equals negative 1, right? Because this part was not removable. You're specifically looking at things that make the bottom 0. Can you remove them? Can you not remove them? The x minus 2 I could remove. It's not going to leave an asymptote. It's just going to leave a hole in the graph. The x plus 1 is not removable, and so it is going to be an asymptote. If you did the same thing to this function I have listed down here, this is similar to one that we saw at the beginning. The bottom is just not factorable, right? The bottom is just not factorable. So there are no discontinuities. The domain is from negative infinity to infinity, and there are no vertical asymptotes. This rule that we're looking at right now is how to find vertical asymptotes, not horizontal, right? And so to find vertical asymptotes, this is the only real example that I have of this. The way to find vertical asymptotes, you factor the top, factor the bottom. You're looking for things that make the bottom 0, and then specifically, if it can be removed, it's not an asymptote. If it can be removed from the top and bottom, it's not an asymptote. It's a hole. If it cannot be removed, and it's still on bottom, like this x plus 1 here, then it is an asymptote. That x plus 1 was not removable. It could not be removed, so then we'll have an asymptote at x equals negative 1. Whatever would make that 0, right? We're trying to avoid things that make the bottom 0. Negative 1 would make the bottom 0 there. All right, horizontal asymptotes. Here's the definition of a horizontal asymptote. It's where your function value, your y value, approaches a number as x approaches infinity or negative infinity. So that means as I go far off to the left or right, your function value flattens out. So like this, if I'm going to the left and your function flattens out, that's a horizontal asymptote. Same thing, going to the left, flattens out. Going to the right, flattens out. Going to the right, flattens out. That's not, if I had something that was going upwards, whatever, that's not flattening out, right? It has to be flattening out towards that end. Horizontal asymptotes have this one quirk that you can cross over them, but they still act like the rain gutter analogy that I was talking about, where even if it crosses over, it's still going to stay in that rain gutter. All right, the way that you identify horizontal asymptotes, there's a three-piece method here, okay? I have the actual math definitions here, but I'm going to try and simplify that here for you in the bottom. There's a three-part process. And what you're going to look at is the degree on the top and the degree on the bottom. That's the highest exponent on the top and the highest exponent on the bottom. So if the top has a higher degree, so this is something like f of x equals 7x to the fifth plus blah, 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 over 3x squared plus blah, 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 blah. If the top has a higher exponent, then there's no horizontal asymptote. In fact, there's probably a slant asymptote, which you will not have to find for this class. There's a slant asymptote. All right, if the bottom has a higher degree, so that would be something like (7x squared over 3x to the fifth). The bottom has a higher exponent than our slant asymptote, our horizontal asymptote. Is at y equals 0 every single time. If the bottom has a higher degree, your horizontal asymptote is going to be at y equals 0. If they're equal degree, so that would be something like f of x equals 7x to the 3 over 4x to the 3. Anything else can happen, but the highest exponent is the 3, top and bottom. If they have the same exponent, top and bottom, then you have a line that's y equals a over b, where a over b are your leading coefficients. So this would be, for example, a horizontal asymptote at y equals, and you're looking at the leading coefficients. So it's just going to be the 7 over 4. You're just looking at the leading coefficients. If you could simplify that, you would. So if it was 8 over 4, you'd just say y equals 2, right? That only happens if they have an equal degree. So you're going to land in one of these three cases. Case 1 is where the top has a higher degree and you have no horizontal asymptote. You just have a slant asymptote. You won't have to find it. You're just going to say there is not one. There's not a horizontal asymptote. Case 2, the easiest, when the bottom has a higher degree, your horizontal asymptote's at y equals 0. Or case 3, where they have equal degree, and then you're just looking at their leading coefficients to find y equals that is going to be your horizontal asymptote. All right, here we go. I said this earlier, a rational function can have a whole lot of vertical asymptotes, but it's only going to have one horizontal asymptote, if it even has one. It has at most one. It either has one or it doesn't have one at all. All right, find the horizontal asymptotes. For part A, we're looking, does it fit case A, case 1, case 2, case 3? That one fits case 3. The bottom has a higher degree. The bottom has a higher degree. I'm sorry, case 2. Case 2. The bottom has a higher degree. So then our horizontal asymptote is at y equals 0. B, higher degree on top. That's case 1. No horizontal asymptote. And C, they both have an x squared, so that fits case 3. Then our horizontal asymptote is at y equals, remember we're looking at the leading coefficients here, so that would be 8 over 2. That's the same thing as y equals 4. This again is identifying horizontal asymptotes. For each of these, you would look at the bottom, try and make the bottom 0 to find your vertical asymptotes. With all of that information, you can go and get a pretty healthy idea of what the graph is going to look like. This example 6 says we're identifying all of the asymptotes of a rational function. We want to identify all of the asymptotes. I've already done the heavy lifting over here of factoring the top. And so we can rewrite this as f of x equals x minus 3, 2x plus 1 over x minus 2. All right. For our horizontal asymptotes, I'm actually going to look at my original problem. Since the top has a higher degree, that fits into case 1, and there's going to be no horizontal asymptotes. For our vertical asymptotes, I'm looking at the bottom. X cannot equal 2, right? The question is that removable? No, it is not removable. So then there's a vertical asymptote at x equals 2. We're going to look more at graphing these next class, but whenever you go to graph it now, what you would do is you would place your asymptotes before doing anything else. So x equals 2, I would put my dashed line there and say the graph is not going to cross that vertical asymptote. It can do anything on the left, anything on the right. I have no idea what it does, but I know that it doesn't cross that line. That also tells me some things about limits. So if I looked at, for example, as x approaches 2 from the left, then f of x, because that's a vertical asymptote, is going to either approach infinity or negative infinity. I'm not sure which because I haven't graphed it. The same thing as x approaches 2 from the right, because this is the way we defined our vertical asymptote. A vertical asymptote is a place where f of x is going to go to infinity or negative infinity. I know those two things are true because of the vertical asymptote. So I know that my graph is probably going to look like something like this, like this, like this. It's going to go towards infinity at 2. I'm not sure which way it's going to go, but it's going to go towards either positive or negative infinity at these places as we approach 2 from the right and as we approach 2 from the left. All right, that's the intro to rational functions. We're going to keep studying rational functions. We're going to learn a whole lot more about them in the next lesson.